I think we can get started. It's 8. Good morning, everyone. It is a great pleasure to have you here and to welcome you to this first edition of our course on time-varying functional connectivity. We have decided together with Vince to organize this course this year because we felt we now have sufficient insights to understand which are the most promising methods and how these methods can be used to improve our understanding of brain function. So the core goals of this course will be first to provide you with the basic methodological background to understand the properties of the different methods that have been proposed. We will then also help you to build a neuroscientific interpretation of these different methods and the corresponding properties. And we will finally guide you through different toolboxes that have been developed recently and that now allow to have powerful analysis of functional connectivity dynamics. So before going to my talk, let me briefly come back to the motivation of time-varying functional connectivity. To this end, let's get back to the basics being that we are studying the brain and we want to know how this brain functions. So we collect some functional data that typically looks like this and that consists in different time series that reflect more or less directly the level of neuronal activity in different regions in the brain. Then from this dataset, we can compute what we call functional connectivity that was defined as the statistical dependence between different time series. And until recently, the most classical way to compute this statistical dependence was to use the correlation of this entire dataset. So if you compute the correlation from the dataset, you end up with a matrix, a square matrix, that encodes the level of correlation of all the pairs of regions of interest. But then people, among which Vince, have said, wait, but what happens if we compute this correlation at different moments in time? So for example, what happens if I compute this correlation in a first window at the beginning of the time course and that I then slide this window over the entire time course? What happens is the following, and we observe some temporal fluctuations of this correlation between different pairs of regions of interest. So here the blue curves correspond to the correlation time courses between that reflect the correlation between pairs of regions of interest, and the red curve is the average of the blue curves. And here we see that the brain exhibits different functional connectivity patterns. For example, in the middle of the scan, the connectivity seems to be on average higher, and at the end of the scan, we have on average lower connectivity. And it's this comparison between, on the one hand, the fact that we assume that all the functional connectivity information can be encoded in a single correlation matrix, and on the other hand, the fact that we do observe fluctuations of this quantity, of this correlation, that has triggered the development of and the extension of the classical way of computing functional connectivity that we will call static functional connectivity towards new methods that encode this temporal information. This will be the topic of the course, and the outline is as follows. So during the first part of the talk, we will provide you with some basic terminology about dynamic functional connectivity to basically understand what's going on. So I will be doing this. Then Julia and Vince will go into more details, in the details of the different methods and the different families of methods that have been proposed to extend this static representation of functional connectivity. In the second part of the course, Michael and Jessica will discuss the different interpretations we can have of functional connectivity dynamics, and they will have two different perspectives. So Michael will relate the fluctuations that we observe at the brain scale level, typically what we observed in fMRI data or EEG data, and we'll relate these fluctuations to neuronal level fluctuations. So in other words, he will try to relate the cellular level and try to explain how these properties generate whole brain dynamics. And Jessica will focus on the behavioral interpretation of functional connectivity dynamics. Then Timothy will summarize the course and maybe also point to some questions that are still debated in the field that still need to be resolved. So I also wanted to take this opportunity to thank all the speakers, all these speakers who accepted to contribute to this first edition of the course. From a more practical point of view, and as mentioned in the first slide, we will offer some hands-on demonstrations. And for those of you who are interested in following in live what's going on, I invite you to download the toolboxes that are available from the course webpage, and the link to the course webpage is available from the course, from the conference program. We also set a hashtag. So if you have any question on a specific talk or on the whole course now or even later during the conference, don't hesitate to ask this question. We'll try to address it during the talk or maybe later on. Okay, so I think we are now all set to move to my talk, in which I will first discuss the main ways of extending this classical static representation of functional connectivity. And to understand how we can extend and define new ways of computing functional connectivity, we first need to understand the properties that are attached to this way of computing functional connectivity. In other words, the properties that are attached to the correlation as a measure of statistical dependence. A first property is the fact that it's an average measure. This simply comes from the fact that we compute the correlation over the entire fMRI time series. And another property of correlation is the fact that it's a memoryless measure of statistical dependence. And I will come back in the next slides on what it means, what I mean by memoryless. And depending on which one of these two properties you are relaxing, you will define new ways and different ways of extending static functional connectivity. So for example, if you relax the averaged assumption, you will be doing what we will refer to as time-varying functional connectivity. On the other hand, if you relax the memoryless assumption, you will be doing what we will refer to as dynamic functional connectivity. And here I should mention the fact that different definitions for these terms, static, dynamic, time-varying, have been proposed in the literature. We don't claim that these definitions are the only definitions that are valid. But what we say is that it's important to have a consistent terminology and to have a clear understanding of the different terms that we use in order to understand what we say and to avoid confusions when talking about functional connectivity dynamics. So in this course, we will try as much as possible to stick to these definitions. Coming back to the slides, a lot of attention has been devoted to time-varying approaches. And this one is, I would say, the most intuitive. That's typically what you do when you measure a certain quantity at different time points, because you relax the average assumption. So when you have a sliding window approach, you are having a time-varying approach and measure of functional connectivity. So I won't spend too much time on this because I think it's quite intuitive, and I will rather spend a few minutes on explaining the difference between a memoryless and a dynamic approach and measure of functional connectivity. So to understand the distinction between the two, let's use a small toy example, and let's assume that we are astronomers. So we are astronomers provided with a sequence of different snapshots of the sun in the sky at different moments in the day. And we know that the first one was taken in the morning, the second one at noon, the third one in the afternoon, and the last one in the evening. We are now asked to come up with a description of the motion of the sun in the sky during the day. From this sequence of snapshots, it seems quite easy to come up with a description that would be something like this. The sun basically moves from left to right. Let's now assume that instead of being provided with this sequence of snapshots, we are provided with a randomly shuffled version of these snapshots. And we now don't know anymore when each picture was taken. In this case, if we are asked to come up with a description of the motion of the sun, it seems much harder to come up with a satisfactory explanation and description of this motion. So what is the difference between the two cases? Well, in the first case, we have access to the temporal ordering information. And that's essentially the difference between a memoryless and, which is the first case, so these authors call it static, and a dynamic approach. So in a dynamic approach, we have access to this, to the temporal ordering information. We know which data set comes before the next one, and we exploit this information. So this was for the toy example. Let's come back to our application and the case of correlation. I've mentioned the fact that the correlation is a memoryless measure of a statistical dependence. It might be obvious to some of you, but in order to make it obvious to everyone, let's check it experimentally. It can be done quite easily. So we have our dataset and we are computing a correlation between two time series. We focus on two time series, we denote the time series x and y, we compute a correlation, and we get a certain value, 0.5349. Let's now modify these original time series by randomly shuffling all the time points. And we get a different dataset, which looks as follows. And we now compute, again, the correlation between x tilde and y tilde. What do we get? Well, we get exactly the same value. And there is nothing very mathematically involved here, but whatever the shuffling, it's easy to show that you will always get the same value of the correlation. And that's actually very important, because it means that in the original fMRI or EEG time series, you have temporal ordering information that you put to the trash if you use the correlation as a measure of functional connectivity. Okay, so to summarize the different ways of extending the static approach, if we relax the averaged assumption, then we are doing time-varying functional connectivity. That's what we do when we have a sliding window approach, and when we, for example, explore how the brain switches between different states. I would also classify CAPS in this family of approaches and other methods, but I won't give further details here because Julia and Vince will elaborate more on these topics. On the other hand, if we exploit the memory of the time series, we are doing dynamic functional connectivity. And the simplest way to do dynamic functional connectivity is to use an autoregressive model. At least a simple way to do it. I wouldn't say it's the simplest way. But a simple way to do it is to use autoregressive model of fMRI time series. So an autoregressive model, a first order autoregressive model looks like this, where xt is the fMRI volume at time t. A is a model parameter that models the link between fMRI volumes at successive time points, and epsilon is the residual of the model. And the temporal ordering information here is encoded in the link that we explicitly make between successive time points. The matrix A has the same size as a correlation matrix. It's also a square matrix that can be seen as a dynamic version of the correlation. So I won't elaborate too much on this specific model now, but for those who are interested, on Tuesday morning there is a symposium on dynamic functional connectivity during which we will discuss how the autoregressive model can be used to extract behavioral information from resting state fMRI data. This is for Tuesday morning. So, as I said, the autoregressive model is a very simple way to exploit dynamic information from fMRI time series, and essentially a lot of information theory measures also exploit this information, such as grandeur causality or transfer entropy, that essentially exploit the information encoded in autoregressive model of fMRI time series. We can also classify in this category all the spectral approaches, because you can again see it quite easily if you shuffle the time points and you compute again a spectrum of this shuffled version of the dataset, you will completely change the spectrum. So the spectrum is also exploiting this temporal ordering information. And another way to view this is that if you shuffle the elements of a cosine or a sine, you don't have a cosine or a sine, etc. As I said, Julia and Vince will further elaborate on these different models. I will now address a question that arises when that has led to a lot of confusion, I think, in this field, and that arises when looking at the following picture. So we can take some time to look at the picture, and a question that we might have when looking at this is to know whether we need different models of the data to model what's happening at different moments in time during the scan. So for example, do we need a different model in the middle here, where we have on average a very highly connected brain, versus the end of the scan where the connections seem to be weaker? In other words, does observing temporal fluctuations call for the use of time-varying models, or models with parameters that are not constant in time? Well, to explore this question, let's use again a toy example and assume this time that we are archers. So I'm an archer and I'm shooting arrows to a target. Let me denote by dt the distance of my hit to the center of the target, and by r the radius of this target. We can assume that for some categories of archers, the probability distribution of this distance, dt, follows a uniform distribution between 0 and r. A first important thing to note here is that this model has constant parameters. So that means that for each shoot at the target, I will have a same probability distribution for the distance of my hit to the center of the target. So if this is clear, let's now go to the next step, which is to start shooting at the target. So I shoot the first time and I get a hit with a certain distance to the center. I do it a second time, I get another distance, etc. I do it several times, and this is what I get. So first important thing to realize here is that these fluctuations are real. They correspond, they capture a physical quantity, which is the distance to the center of the target. And so the second thing to point at here is the fact that we don't need different models to model trials where I'm close to the centers and trials where I'm hitting far from the centers. So we don't need different models of the archer here and here, for example. And so this actually directly answers our question, our initial question. A priori, we don't need different models to model what's happening when the brain is highly connected versus when it's weakly connected. This was for the toy example, and let's now come back to our application, which is, again, focusing on functional data and time series. What are we doing when we have a static representation of functional connectivity? So we use the correlation and we assume that all the functional connectivity information is encoded in this single correlation matrix. Another way of framing this is that what we do is to assume that fMRI time series, fMRI data, are generated by a Gaussian distribution that has a mean 0 and a covariance or a correlation equal to C, C being the sample covariance measured from the data. As for the previous slide, this model has constant parameters. So the parameters are the same for each time point. And if you now generate data from this model, which is actually a null model for those who are familiar with null models theory, if we generate data and then apply a sliding window correlation on these generated data, we get this, where the blue curves again represent the correlation time series between different regions of interest, and the red curve is the average of these blue curves. And again, here, these fluctuations might be capturing something that is real. And an important thing to notice here is that the fluctuations are not spurious a priori. It's not just noise that is fluctuating across C that would mean nothing. It might mean something. But then you will say, okay, maybe it's meaning something, but it doesn't look at all like what we observe in real fMRI data. And you are completely correct. If we apply a sliding window correlation on real fMRI data, this is typically what we would observe. And if we compare fluctuations that we observe in real data and fluctuations that we see in data generated by a static model, comparing the two, it's possible to show, for example, based on the variance of the red curve, that these two are different. So another way of framing this is that we are missing some statistical properties that are included in fMRI data if we use a static representation of functional connectivity. But here comes dynamical models into play. If we now, instead of assuming that fMRI data are generated by a Gaussian distribution with this covariance pattern, if we assume that fMRI data are generated by an autoregressive model, this is what we have. And again, every time point is generated by the same model, right? So the parameters are constant. Let's assume we now generate again data in the same way we did it for the static model. From this is what we get. And in this case, we've shown in this paper that it's much harder to distinguish the two. I'm not saying that it's impossible. Based on some statistic, we can make a difference between the two, but it's much harder to distinguish real fluctuations we observe in real data from fluctuations that we observe in data generated by a first-order autoregressive model, hence with constant parameters. And this is very important because it means that even if we observe temporal fluctuations, we can use a model with constant parameters that seems to be capturing most of these temporal fluctuations and statistical properties that we observe. Okay, let me now summarize the different properties and the pros and cons of time varying versus dynamic approaches. If I had to summarize the main pros and cons, I would say the following. A time-varying approach is essentially exploiting the time-resolved information that you have in the data. So for example, if you use a sliding window and then cluster the results into different states, you can ask in which state the subject was at time 100, for example. This is some information you might not have access to if you use a dynamic approach. For example, if you use an autoregressive model, you might not know this information. But the price to pay to have access to this time-resolved information is that you will have a much more complex model of the data, because you need different models at different time points, whereas in the dynamic case, if you use a first-order autoregressive model, you have a very concise representation of the dynamics that you observe in the data. So it really depends on the application that you are considering, and I would say there are different cases where time varying would be preferable and other cases where dynamic representation would be more adequate. Okay, with this I would like to conclude and articulate the conclusion around 3 points. The first one is the importance of nomenclature. As already mentioned, you've seen here that sometimes we can be challenged by our intuition, and it's important to have a clear definition of the terms that we are using. So I hope you here have a better understanding, at least, of these different terms. But it's important to clarify these terms in order to be able to discuss with each other and to understand what we are doing and in which category of methods the method that we use belongs. A second thing is that I hope I've clarified the difference between a time-varying approach versus a dynamic approach. The first one is essentially exploiting the time-resolved information, whereas the second one is exploiting the memory of the system. So these are two very different approaches from a conceptual point of view. And then I finally also wanted to say a word about things that I did not detail in these presentations, such as null models. So I felt that the use of null models is, well, very important, but maybe beyond the scope of this talk and this course. But null models are very important to characterize the dynamical properties of functional connectivity. And essentially what we have done when we have compared the fluctuations observed in real data versus the fluctuations observed in data generated by a static and a dynamical model, this was essentially null model testing. For those who are interested in knowing more about null models, Andrew Zaleski will talk about this again in the same symposium on Tuesday morning. I also did not talk about stationarity. So this has been a hot topic in the last years in the field. And actually, and this relates to the first point, if we come back to the definition of stationarity, stationarity is a property, a statistical property that goes with many different models that have different properties. So for example, Gaussian noise is stationary. An autoregressive model under mild assumptions is also stationary. A hidden Markov model is stationary. And so in my opinion, stationarity is not really informative and does not allow to have a finer description of functional connectivity properties. So it's important to know what it is. But if we stick to the definition, it is, in my opinion, not the most important property to describe functional connectivity dynamics. These terms, static, time varying, memoryless dynamic, are, in my opinion, more important. And then I also did not go too much into the details of first order versus second order statistics. So second order statistics are essentially the correlation and the covariance, whereas first order statistics are the mean and the real time series, I would say. The reason for this is that this dichotomy that I presented between time varying and dynamic applies whatever the statistics you use. And so people have been using second order statistics most often to describe functional connectivity. But some people have also now recently used first order measures to explore functional connectivity properties. But again, it's important to realize this distinction, but the dichotomy between time varying and dynamic applies whatever the statistics you use. I would like finally to mention some references. The first paper is a paper we wrote last year that essentially covers this presentation and also includes some results on stationarity for those who want to know more about stationarity. Some results also about null models. And for those who want to know more about dynamic versus memoryless system, I would suggest you to go through these two other references that provide more details about the properties of these two types of models. I also want to thank my collaborators on this paper, and in particular Thomas here at NUS, who has been supervising the paper, and I thank you for your attention. Do you have any question? Yes?
I'm sorry for the question, but I would like to know, maybe I missed the definition about dynamics, but how can we be sure that it's not just motion if we measure, I mean, we go into time with
Well, that's a very important question, and to test this, we can. So, for example, what we did in the paper is to only focus on the subjects with very low motion. So we used the S900 dataset, and we used the 100 subjects with the least motion. And so it seems that even in subjects with almost no motion, we do observe these fluctuations. And so there seems to be an intrinsic dynamics of functional connectivity. And so I would say we need to be careful about that and to. Yes, sure. Mm-hmm. Well, so when you have higher motion, you typically see jumps and in these functional connectivity measures, and in this case an autoregressive model seems to not capture these jumps anymore. But for subjects where you don't have motion, where you have real fluctuations and intrinsic fluctuations that are not due to motion, then the autoregressive model seems to be capturing that quite well. But we do see differences between subjects that didn't move a lot and subjects that moved a lot. The pattern of functional connectivity? So I'm not sure what you. Okay, I cannot come back. I'm not sure what you mean by pattern, but for example, you see these fluctuations that I showed. The amplitude of the variance of the red curve was related to motion, for example. It was bigger on average in subjects with that moved more, which seems. Yes?
Could you also compare between brain regions that are supposed to be not dynamical in the sense, or less highly connected to other brain regions versus brain regions that are supposed to be highly connected across, I don't know, across the time series?
So that's definitely also a question of interest. We did not explore systematically all the regions, but what we did do is to test whether different null models are able to reproduce the connections between pairwise connections. And again, if you have an atlas with 100 regions, typically the one of Thomas Yeo 2011, you have something like 6,000 connections. And out of these 6,000 connections, on average, you find 10 or 15 connections that cannot be represented by an autoregressive model, because the fluctuations are bigger than what you expect in a dynamic model, in an autoregressive model. Yes?
What are the assumptions between an autoregressive model and ICA performed in the time domain? Would those give you similar explanation of temporal clusters? I know ICA also depends on non-stationarity. I think that's one of the assumptions.
On non-stationarity? Well, I wouldn't say it depends on non-stationarity because, well, okay, let's not talk about stationarity. But I'm not sure you can use ICA to create models of the data, to generate data, for example. So the approach, and conceptually the approaches are different. So in an autoregressive model, you explicitly look at how time point 10 influences time point 11. So that's the information that you exploit, whereas in ICA you exploit non-Gaussianity essentially, and temporal non-Gaussianity if you do it in the temporal domain. But it's more a method. It's more method-driven, whereas an autoregressive approach is essentially model-driven. So I would say conceptually it's quite different, and you don't reach the same conclusions. Thank you. Is there a last question? No? Okay. Thank you for your attention. I will now leave the floor to Julia from the École Polytechnique Fédérale de Lausanne in Switzerland. So, yes?